used to describe the laws of transverse vibrations of a string. Let's do that. Now, first law says the fundamental frequency of vibration of a stretched string is inversely proportional to the length. Is that right? The length is on the denominator. If all these other quantities are kept constant, in other words, the tension and the mass per unit length are constant, then the frequency is inversely proportional to the length. It means as the length of the string becomes shorter and shorter, the frequency becomes higher and higher. Is that right? Yes. If you look inside your piano, the highest frequency is produced by the shortest wire, and the lowest frequency is produced by the longest wire. Frequency of the fundamental mode of vibration is inversely proportional to the length of the string when the tension and the linear density are constant. The second law says for a given length, if length and the value of mu, well, mu actually describes the thickness of the wire. If length and mu are kept constant, then the frequency is directly proportional to the square root of the tension. And that is the second law. Third law is the frequency is inversely proportional to the square root of mu. That means a thicker wire will produce a lower frequency. So these are the three statements of the laws of transverse vibrations of a string. You must be familiar with those three laws. The fundamental frequency of a stretched string is, you know this, F1 equal to 1 over 2L square root T over mu. And when the string vibrates in its second harmonic, look at this, lambda will be equal to L. So what will be the equation for that then? F2 equal to 1 over L times square root T over mu. And this is equal to actually twice the fundamental. You know that. Similarly, the frequency of the third harmonic will be 3 times the fundamental. Well, all these information we already know. All right. The fourth harmonic. Now, the higher harmonics are also called overtones. Overtones. The second harmonic is called the first overtone. The third harmonic is called the second overtone, and so on. So, overtones are higher harmonics. Let's now solve a couple of problems. A string fixed at both ends is 3 meters long. It resonates in its second harmonic at a frequency of 60 Hertz. 60 Hertz is the frequency of the second harmonic. What is the speed of transverse waves on the string? Well, let's pick out our data. L equal to 3 meters. The frequency of the second harmonic, watch that, F2 equal to 60 Hertz. The string vibrating in its second harmonic vibrates in 2 loops, like this. That means since the length of 2 loops equal to 1 wavelength, length 3 meters gives you a measure of the wavelength of that wave. So what is the wavelength of the wave here? The wavelength of the wave equal to the length of the string, which is therefore 3 meters. And now, what are we supposed to find? Speed of the transverse wave. Well, speed equal to V equal to F lambda. We know the frequency of the second harmonic. We know the wavelength of the second harmonic. Therefore, we can calculate the wave speed. So wavelength equal to 3 meter, V equal to F lambda, that will be 60 hertz times 3 meter, that is 180 meter per second is the wave speed. Alright, another one. The wave function yxt for a certain standing wave on a string fixed at both ends is given by this. Now, do you remember the general wave form of a stationary wave? Yes, it will be y equal to a sine kx cos omega t. You see that? A sine 2a, is that right? 2a sine kx cos omega t. You can see that is the wave function given to you. What are the speed and amplitude of the two waves that result in the standing wave? What is the distance between successive nodes on the string? Remember, the distance between successive nodes is equal to half of the wavelength. So if you know the wavelength, then you know the distance between successive nodes. What is the shortest possible length of the string? Well, the shortest possible length of the string will be the distance between two nodes, because that is the lowest mode of vibration. Okay, let's do this problem. The general equation for a standing wave on a string is y equal to 2a sine kx cos omega t. That means compare this with the given equation. 2a equal to 0.05 meter, k equal to 2.5, is that right? Kx, 2.5x. K equal to 2.5, omega equal to 500. You can see how the wealth of information contained in the equation of the wave. A is the amplitude, k equal to 2 pi by lambda is the wave number, and omega equal to 2 pi f. Alright, let's now pick the values and do this problem. Comparing the general equation to the equation of the wave, we have 2a equal to 0.05 meter. That gives you A, the amplitude of each wave is 0.025 meter. You got k equal to 2.5, but k is 2 pi by lambda. So 2 pi by lambda equal to 2.5. We can obtain wavelength right away from there. So wavelength lambda equal to 2 pi divided by 2.5, and that will be, well, I didn't calculate that. You can calculate that on your own. What is that 2 pi divided by 2.5? And 2 pi f omega, this quantity is omega, which is 2 pi f equal to 500. Therefore, f equal to 500 divided by 2 pi. Well, I left these without calculating because I'm going to use them to find this quantity. What do I need to find? Speed. How do I find the speed? V equal to f lambda. So V equal to f lambda. F is 500 over 2 pi. Lambda is 2 pi divided by 2.5. There you are. And you know why I did not calculate those values. You can see 2 pi and 2 pi will cancel in both cases. Therefore, V equal to 500 divided by 2.5. That is 200 meter per second. Alright, let's now go and do the B part. What is the distance between successive nodes on the string? Well, what did I say the distance between two successive nodes is? The distance between two successive nodes is half of a wavelength. Distance between successive nodes is 1/2 of the wavelength. Now, this is the distance between two successive nodes. That is a node, that is a node, and that distance is half a wavelength. And wavelength we know, and therefore we know that distance. Lambda equal to 2 pi divided by 2.5, therefore lambda by 2 equal to 2 pi divided by 5. And the distance between successive nodes is therefore 2 pi divided by 5 meter. Can you answer the last part? I have actually answered that for you. What is the shortest possible length of the string? Well, this is the shortest possible length of the string, which is 2 pi divided by 5. Since the fundamental is the lowest mode of vibration, the string must have a minimum of 2 nodes when it vibrates. It cannot have anything less than that. So this is the shortest possible length of the string, which is 2 pi divided by 5. That is 1.26 meter. Okay? Let's do another one.